Hello, welcome to another module in this massive open online course on estimation for wireless communications. So far we have looked at various techniques of estimation, basically various techniques of estimation to overcome inter-symbol interference. First we have seen time domain equalization, that is basically based on zero forcing, the zero forcing equalizer, and we have also seen a very low complexity equalizer, that is OFDM, that is orthogonal frequency division multiplexing. It is not equalization, but it is an interesting and very efficient transmission scheme. Now today we are going to look at yet another scheme which is termed as frequency domain equalization for ISI, that is removing inter-symbol interference. So starting today we are going to look at what is known as FDE, which stands for frequency domain and naturally it is equalization. Remember, equalization is where we remove, this is for equalization is for ISI removal, that is it is to remove the inter-symbol interference. And previously we have seen two different techniques. So this is FDE, which is frequency domain equalization. Previously we have seen time domain, that is equalization in the time domain, that is your zero forcing equalizer. This is one of the techniques that we have seen. Let us call it technique 1. Technique 2 is basically your OFDM or orthogonal frequency division. Orthogonal frequency division orthogonal frequency division multiplexing, and this is basically the third technique that we are going to look at now, that is termed as FDE or frequency domain equalization. And as the name implies, this is where basically equalization is done in the frequency domain, that is previously we have seen zero forcing equalization, where basically equalization is done in the time domain, alright. This is now frequency domain equalization, where equalization is done in the frequency domain, alright. And it is very similar to OFDM, although there is a very important, very subtle yet a very important difference with respect to that of OFDM or orthogonal frequency division multiplexing. So let us see what is the mechanism for this FDE, that is frequency division or frequency domain equalization for removal of ISI. Okay. So in FDE, that is frequency domain equalizer, so let me just write this again because we are talking about FDE, that is frequency domain equalizer. What we have is basically, instead of transmitting loading symbols on the subcarriers, we do not load the symbols on the subcarriers, but we transmit the symbols directly, that is x0, x1, x2, x3. Let us say these are the block of symbols, these are the n equal to 4 symbols, right. These are not the samples, but these are, remember in OFDM these are the small x's in OFDM are the time domain samples which are generated by the IFFT of the symbols loaded onto the subcarriers. However, in FDE we directly transmit the symbols, so there is no loading of the symbols on the subcarriers. Instead, the small x's, small x0, small x1, small x2, small x3, these are the symbols. These are the symbols which are directly transmitted with one modification, that is adding the cyclic prefix. So we add the cyclic prefix. So in that sense, it is similar to OFDM, that is we take x3 which is from the end and we prefix it at the head of the block. This is termed as the cyclic prefix. This is something that we have seen it several times. And now this cyclic prefix, so these are the time domain symbols. So now these are not the time domain samples, but these are the time domain symbols, that is BPSK or QPSK or so on, basically modulated symbols, plus the cyclic prefix. So, the cyclic prefix added block of time domain symbols. Now, this is transmitted across the ISI channel, and remember ISI stands for inter-symbol. ISI stands for inter-symbol. ISI stands for inter-symbol interference. Yeah. So, this is transmitted across the ISI channel. Remember, our model for the ISI channel is the same. We are considering the 2-tap ISI channel, which is basically your YK, current symbol YK, current output symbol is H0, XK plus H1, XK minus 1 plus Vk. Remember, what is this? This is your 2-tap. This is your 2-tap ISI channel or 2-tap inter-symbol interference channel, all right. Okay. And now, when we transmit this symbols, time domain symbols with cyclic prefix, of course, the effect of the channel is that of circular convolution. Therefore, I will have Y, which is H, the channel filter circularly convolved with X plus V. Why does this arise? This arises because we are transmitting, well, arises due to basically addition of this arises because of the addition of the cyclic prefix, and this is something that we have seen several times before. That is, I take a block of samples, add a cyclic prefix and transmit it across an inter-symbol interference channel. The output Y can be modeled as basically the channel H circularly convolved with this block of symbols, yeah, or samples, whichever are transmitted, plus in the presence of additive noise. Okay. So, naturally, once we take the FFT, in the FFT domain across each subcarrier or across each kth frequency point, it is going to be the multiplication in the of the channel FFT coefficient and basically the FFT coefficient of these symbols that are transmitted in the time domain. Okay. So, now once we take the FFT, taking the FFT of the output, we have across the Lth subcarrier YL, that is, if I look at this across the Lth subcarrier, I have YL equals HL times XL plus VL. What is this? This is across the Lth subcarrier, yeah, taking the FFT across the Lth subcarrier. In fact, YL is the output symbol across the Lth subcarrier, HL is the channel coefficient across the Lth subcarrier, XL is basically your symbol transmitted on the, that is basically, now this is basically not the symbol on the Lth subcarrier, but this XL is the Lth FFT point of the symbols. This is simply now the Lth FFT point of symbols. Remember, because we are transmitting the symbols in the time domain, this is the Lth FFT point of the symbols x0, x1, x2, x3, and VL is basically your Lth FFT point of the noise samples. Okay. Okay. So, now let us explore this quantity capital XL again. XL, as we said, is the Lth FFT point, this is the Lth, this is the Lth FFT point of your transmitted symbols, that is the symbols in the symbols, that is basically your symbols are the x case, yeah, the small x case, which are the small x case in the time domain, which means basically your XL is the n point FFT of, that is how do we generate these XLs, that is basically you have your symbols in the time domain x0, x1, x2, x3, and you take, now what are these in the context of FDE, these are the time domain symbols. So, in FDE, remember previously in OFDM these were the time domain samples and these are generated by the IFFT of the symbols loaded on the subcarriers. However, in FDE the important difference is these are not the time domain samples, but these are the time domain symbols, because we are directly transmitting the symbols in the time domain after adding the cyclic prefix rather than generating the samples. Okay. So, once we take the FFT of this, that is the n equal to 4 point FFT, what we have is simply the capital XLs, which are simply the FFT coefficients of the transmitted symbols. So, what we have is, now we are looking at, we take the n equal to 4 point FFT of this, and what we get are basically we get the capital Xs, which are x0, x1, x2, x3, and these are simply your frequency domain FFT coefficients of the time domain symbols. These are not, these are simply the frequency domain, and that is the important difference with respect to OFDM. These are simply the frequency domain FFT coefficients of your the time domain symbols, which are the small x xk. In fact, your capital XL equals, that is the Lth FFT point summation k equal to 0 to n minus 1 small x k e raised to minus j 2 pi k L divided by n, substituting n equal to 4, since we are considering a system with n equal to basically 4. Therefore, what we have, this is basically equal to summation k equal to 0 to 3 x k e raised to minus j pi by 2 k L. Okay. So, XL is the Lth FFT point. So, what is XL? XL is the Lth FFT point of the time domain transmitted symbols. What is this? This is the Lth FFT point Lth FFT point of the time domain symbols, okay, that is XL, and the rest are again same. That is, if you look at the capital YLs, which are basically generated by the FFT of the time domain output symbols, that is basically you have the small YLs, yeah, the small y case y0, y1, y2, y3, and you take the n equal to 4 point FFT, you get the capital Y0, capital 1, capital Y2, capital. These are the n point FFT of the time domain output sample, the time domain output symbols that are received. These will give the FFT of the time domain output symbols gives the frequency domain output symbols across each subcarrier, okay, across each FFT point. Okay. So, what we have is you have y0, y1, y2, y3, you take the n equal to 4 point FFT, these are time domain output symbols. These are the time domain output symbols, and what you get is y0, y1, y2, y3, and these are basically, these are your frequency domain output samples. Yeah, the frequency, the FFT coefficients of the received time domain symbols. Yeah, you take the FFT of the time domain symbols, that is a small y's, you get the capital Y's, which are the frequency domain output samples, that is a output YL is the output sample across each subcarrier L, or across each frequency point or each Lth frequency point in the FFT domain. Okay. Similarly, now the capital H's are basically the 0 padded FFT of the channel taps. You have L equal to 2 channel taps, you pad n minus L zeros, you take the n equal to 4 point FFT. In fact, this is the 0 padded, this is the 0 padded FFT, you generate the capital H's, H0, H1, H2, H3. What are these? These are basically your frequency domain channel coefficients. These are your frequency domain channel coefficients. Yeah, these are the time domain channel taps, that is something that we have already seen. These are your time domain channel taps. Okay. And finally, of course, you take the small v's, which are the time domain noise samples, yeah, and you take the FFT of these, you generate the capital V's, which are the frequency domain noise samples, that is a noise across each subcarrier L. Okay. So, you take the small v's, which are V0, V1, V2, V3, you take the n equal to 4 point FFT, you get the capital V0, capital V1, capital V2, capital V3. These are basically, what are these? These are basically the frequency domain noise samples across the subcarrier. These are basically the noise samples across the subcarriers, and therefore, now what we have is the frequency domain model across Lth subcarrier or the Lth FFT, the frequency domain model across the Lth FFT point, and that is given as YL equals HL XL plus VL, YL equals HL times XL plus VL. Okay. Now, we can perform frequency domain equalization, that is, one can estimate this Lth FFT coefficient, What is this? Remember, this is the Lth FFT coefficient. Now, we are doing estimation in the frequency domain. We estimate this Lth FFT coefficient. Now, you can see this Lth FFT coefficient can be estimated as x hat L equals y of L divided by h of L. That is what you can see. Yeah, YL equals HL times XL plus VL, and therefore, x hat of L, this is the estimate of the Lth FFT coefficient. This is the estimate of the Lth FFT coefficient. This is equal to YL, which is the output, sample across the Lth subcarrier, and capital HL, which is the channel coefficient across the Lth subcarrier. Therefore, if you do capital YL divided by capital HL, you get the estimate capital X hat L, that is the estimate of the Lth FFT coefficient of the transmitted symbol sequence, which is the small x's. Okay. So, therefore, what we are saying is basically capital X hat 0 equals y of 0, capital Y of 0 divided by capital X h of 0, capital X hat of 1 equals y of 1 divided by x of 1, capital X hat of 2 equals y of 2 divided by h of 2, and capital X hat of 3 equals y of 3 divided by h of 3. Okay. So, these are basically what are these? These are basically your estimates of the basically your x0, x1, capital X0, capital X1, capital X2, capital X3, and these are in turn what are these? These are the FFT coefficients of the symbol sequence, that is small x0, small x1, small x3. And therefore, now what we see is basically you have the small x's, which are the symbols in the time domain. You take the FFT of this, you generate the samples, that is a capital X0, capital X1, capital X2, capital X3. Therefore, from the capital X's, if you perform the IFFT, you can generate the small x's, alright. So, naturally, because the capital X's are the FFT of the small x's, so the small x's are the IFFT, that is you take capital X, you can take capital X at X0, capital X1, capital X2, capital X3, and if you perform the n equal to 4 point, now if you perform the n equal to 4 point IFFT, you generate the symbols in the time domain, and the symbols in the time domain are basically your small x0, small x1, small x2, small x3. So, these are the symbols in the time domain, right. These are the symbols in the time domain. Now, all we have basically, if you can see this, we do not have the capital X's, but we have something close. We have the estimates of the capital X's, we have the estimates of the FFT coefficients, we have the estimates of your FFT coefficients of the symbols, we have the estimates of the FFT coefficients of the symbols. Therefore, if we take the IFFT, what we will get is we will not get the symbols, but rather the estimates of the symbols. So, we will get. So, what we are saying is the samples, that is the capital X's, are generated by the FFT of the symbols, right. So, therefore, if I take the capital X's and perform the IFFT, naturally I can generate the symbols in the time domain. However, what I have is from the frequency domain equalization, basically what I have is I have estimates of the FFT coefficients, the capital X's. Therefore, if I take the IFFT, naturally I can generate the estimates of the symbols, that is the small x's in the time domain. And you can see this equalization is a very simple process. All I have to do is take y0 divide by h0. There is no matrix inversion. So, this is also known as a one tap, a single tap equalizer. Unlike the time domain equalization, that is, if you remember the zero forcing equalizer which was done in the time domain, in the time domain equalization there was a matrix inversion, yeah, depending on what is the order of the equalizer, if you remember. So, in time domain equalization, where basically we are computing the equalizer, there is a matrix inversion that is required. However, in frequency domain equalization, there is no matrix inversion, there is simply a division by the channel coefficient capital HL, that is, we are simply taking the capital YL, which is the output Lth output sample in the frequency domain across the Lth FFT point, dividing it by capital HL, which is the channel coefficient corresponding to the Lth subcarrier, or basically the Lth FFT channel or the Lth FFT point, and capital YL divided by capital HL gives us capital X hat of L, which is an estimate of the Lth FFT coefficient of the transmitted symbol sequence in the time domain. And therefore, now you take this estimates capital X hat of L and you perform the IFFT, and what that gives you is basically that gives you the symbol estimate. So, this is a slightly roundabout fashion, that is, first what we are doing is we are taking a time domain system, moving it into the frequency domain using the FFT, doing the equalization in the frequency domain, and from the equalization done in the frequency domain, we are reconstructing the time domain symbols. Now, we are doing this in a roundabout fashion because, as we have seen, the equalization in the frequency domain is much less complicated. It is simply a one tap equalizer, that is, you have to divide by basically the corresponding channel coefficient on each subcarrier, alright. So, this low complexity motivates us to use equalization in the frequency domain rather than the time domain. And therefore, now naturally what we have is the symbol estimates in the time domain, the X hat X is the IFFT of the capital X hat of L e to the power of j 2 pi k L by n, and now we know this X hat of L is basically equal to y of L divided by h of L. So, which I can substitute now. So, this is basically 1 over n your summation L equal to 0 to n minus 1 y of L divided by h of L times e to the power of j 2 pi k L by n. This is your X hat of k, and that basically gives you, this is your symbol estimate in the capital X hat k, which is the symbol estimate in the time domain. Okay. So, what we have is the symbol estimate in the time domain, and in fact, one can also at this point you can also substitute n equal to 3, n equal to 4. Let us also do that for the sake of completeness. If you substitute n equal to 4, what you will have equals X hat of k equals 1 over 4, that is, for this particular example L equal to 0 to 3 y L divided by h L e to the power of j 2 pi k L divided by 4, which is basically, you can write this as your X hat of k equals 1 over 4 summation L equal to 0 to 3 y L divided by h L e to the power of j 2 pi e to the power of j. In fact, I can directly write this as pi over 2 k L. Okay. So, X hat k is basically your estimate of the kth symbol in the time domain. In fact, this is the symbol estimate, this is the estimate of the kth symbol. Let me also write this x hat k is the estimate of the kth symbol in the time domain. So, basically what we have done in this module is we have started exploring frequency division, frequency domain equalization. We have said that frequency domain equalization is alternative to time domain equalization, which is something that we have already seen before, where we developed the zero forcing equalizer in the time domain. The frequency domain equalizer is basically motivated by its efficiency and its low complexity. So, what we do is we transmit, unlike OFDM where we transmit the samples in the time domain, here we directly transmit the symbols. That is, we take a block of symbols, add the cyclic prefix, and this cyclic prefix added block of symbols is transmitted in the time domain across the ISI channel, that is the intersymbol interference channel. At the output, basically you take the FFT of the received symbols, the small y's in the time domain. You perform, once you perform the FFT of the received symbols in the time domain, you get the output channel, samples, that is the capital Y's in the frequency domain. Using this, you perform frequency domain equalization, that is, you compute the estimates of the capital X hats, which are the estimates of the FFT coefficients of the symbols. That is, each capital X hat L equals YL, that is the Lth FFT point of the received output symbols, divided by capital HL, which is the Lth FFT coefficient of the channel taps, the Lth zero padded FFT coefficient of the channel taps. So, capital YL divided by capital HL gives you capital X hat L, which is the estimate of the Lth FFT point of the transmitted symbols. You take the IFFT now of this capital X hat of L, alright, and once you take the IFFT, that gives you the small x hat of k, that is the estimates of the symbols transmitted in the time domain. So, this is basically frequency domain equalization, which is basically equalization removing the intersymbol interference in the frequency domain, right. At the same time, it has parallels to OFDM, because again it involves both the IFFT and FFT operation. However, yet it is very different from OFDM, and you can go through this module again in detail to understand it better, alright. Okay. So, we will stop this module here, and we will look at an example of FDE, frequency domain equalization, in the subsequent modules. Alright, thank you very much.